Okay, so this lecture this morning we'll look at linear and multiple regression, and it will be our first algorithm that we'll look at of the week. And what we're interested in linear regression, we in the introduction slides before, we were looking at three types of classification, or three types of machine learning, if you like. And the first one of those was, can you predict a continuous variable given other continuous variables? So this is linear regression, or regression in general. So yes, we use regression when we want to assess the effect of one or more independent continuous variables on another continuous variable, or our response variable. And so if we know this relationship, we can predict the value of the dependent variable when given the value of the independent variable. So this is where our prediction comes in. And another good thing about regression is, and this is what it's used for a lot, is if we can understand how much an independent variable impacts the variance in the dependent variable. So we'll cover a few examples just to go over this. But this is what our setup looks like. So we have two continuous variables. So on X, we have our independent variable, and Y, our response or dependent variable, is what we would like to predict. So given a value of X, can we predict what Y will be? And the way we do this is we try to fit a line of best fit through our data. So regression is all about finding a nice line through our data which describes our data. Regression is trying to describe our data. I guess, though, the difficulty comes in where you can have multiple different types, different lines. So, you know, either of these might be, they look like a good fit to us. Maybe we'd be happy to use either of these. Clearly, though, there will be some lines which aren't so good. And really, you could fit almost an infinite number of lines by rotating the lines around, shifting them in certain directions. And the job of linear regression here is to find the best line. So there are practically an infinite number of lines that we could fit. And how do we hone this down? Let's think of how we can measure how well a line fits our data in the first place. So yes, just a comment. Because we're looking at linear regression, we're just looking at a straight line. It's very simple, but you can have other types of regression. It's just polynomial, and we have these nice curved lines and splines and so on. But this is just linear regression today. So here is one line, and intuitively, what can we do? Well, you can measure the distance of a data point along the y-axis from this line, or candidate line, that we're proposing. And this measurement is called a residual, or an error, if you like. I think the terminology is usually residual. And we can actually compute all the residuals from our data points to the line that we've plotted here. So we can kind of measure how far off our line is. It doesn't, you know, a straight line will never describe our data without any error. There will always be some error, but what we're trying to optimize is reduce that error. So again, optimization is going to be a running theme throughout the whole week. So for each data point, we measure the distance, RK, our residual, from the data point to the line. When we take the sum, so we take all of these residuals together and we sum them up, this is called something called SS fit. And you'll notice that some of the residuals, because they pointed down, they were negative. So we square these residuals. We take the sum of squared residuals. This is called something called SS fit. And then that's a really simple calculation. And we're going to do this for, you know, thousands of lines. And because computers are quick, they can do this. So we just repeat this step. And we just take note for each line that we plot, candidate line, we get our SS fit out, the sum of the squared residuals. And the best line of fit is one which will satisfy the sum of the least squared residual sum. So let's talk about this for a second. We have our SS fits for each line. So this is something we can compare amongst all of our lines. And we're going to use a method called linear least squares to determine which was the best. So again, here's our 3 lines, our candidate lines. And let's just say that this is our best from SS fit. We took all of our SS fits together and we just looked at the one which had the lowest SS fit, so the lowest error, which happened to be this line. And that's a simple method called linear least squares. It's really easy. Now, this will also be familiar, should be familiar. Just the equation for a straight line. So we have y equals mx plus c. So m here is the slope. So as you increase m, the slope will become steeper, or you can decrease it and it will start to go from the bottom right to the top left. And c is the y-axis intercept. So this is describing the shift in your line. We could shift this line in certain directions, or even up or down. And you just look at, so C here will indicate this value on the y-axis. And this is good because we now have a line where we can plug in values of x, sorry, an equation where we can plug in values of x and retrieve a predicted value of y. So, we're able to predict things based on our continuous variable x. So this means if you look at the value of m equals 0.8, that tells us that as you increase x by 1, you only increase y by 0.8. And this is the relationship between x and y. So this is really handy thing to work out. And, linear regression gives us this quite nicely. So just to point out, when we look at C, and it's the y-axis intercept, so this is a theoretical minimum. So, the value of C is where x equals 0, and usually in life things aren't 0. So if you think of someone's BMI, no one has a BMI of 0. So therefore, if you look at the value of C in a linear regression, where you're plotting BMI against some response, don't be alarmed if the value of the value of C, our intercept, seems completely unrealistic. That's purely because it's a theoretical minimum where x equals 0. And in that case, we generally don't have people with a BMI of 0. So don't be too alarmed if your value of C just looks pretty strange. But sometimes it can be really useful to indicate an expected minimum. So there we go. That's the first good thing about regression. We can plug values of x into our equation, y equals mx plus c, and predict values of y. Yeah, so there's a worked example there. Now, on to explaining the variance in our response variable. So it might just be that if you were to consider the number of the life expectancy versus the number of cigarettes smoked per day, and obviously we know from evidence that the number of cigarettes you smoke per day is going to impact your life expectancy for a number of reasons. And yeah, so knowing this correlation as humans, we can say, oh well, the more you smoke, the less you'll live, and that's something we would conclude. But we can actually use linear regression to explain the variance in life expectancy if you're plugging in the number of cigarettes smoked per day, i.e., if 80% of the variance of life expectancy is contained within the amount you smoke, then as clinicians, that's actionable. You could then say, well, 80% of the reason why we see lower life expectancy is because of smoking, that you can target that, for intervention. So let's just go back to when we were computing SS fit. So we've calculated all of our residuals. We take the square, we sum them up. Now, what we can do is take the mean of our response variable y and calculate the residuals here. So what you do is you take your residuals of y, and just to compare between residuals in the line of best fit, I hope you can see that we've got these large residuals either side. as you have small values of x and large values of x. But when you sum these up, you should have a larger SS fit, if you like, than our line of best fit. So overall, these residuals will be smaller than if we just took the mean. So i.e., we don't know where the variance comes from. We're assuming that there's no variables that contribute to the variance here. So you see, the larger residuals in just the mean of y. So we can calculate a value SS mean around the mean of y, just as we did with SS fit. So now we have these two objects, so we have SS fit and SS mean. And just as a side, you might hear things like variances. I've already talked about variance. All variances is just the fit divided by the number of data points in your sample. And so we can call these var fit and var mean. They correspond to SS mean and SS fit. And just remember, if you get confused by variances, variance is just literally the sum of squares divided by the sample size. It's just really simple. And all we do is we just subtract the variance var fit from var mean. And this allows us to determine how much of the variance in y is due to the variance in x. So all we do is this. And this r squared is just called r squared. And all it is the variance in the mean minus the variance of fit over the variance in the mean. So we're normalizing by the variance in the mean. And this gives us a percentage. So we have a worked example here. So if you imagine that var mean is 5.5, it's always going to be larger than var fit, which is 2.2. This gives us 60%. So what we would say here is that 60% of the variance in y is due to x, our independent variable. And that's pretty high as far as things go. Usually when you'll be putting in, when we look at multiple regression, you'll be putting in 10, 20, 30 different variables. And you rarely see that one variable on its own will contribute to something this high. But this would be handy because, as I said, you could then say, if we wanted to reduce the variance in y, then x would be a good variable to target to do that. So not only can we use linear regression to predict a single value of y given some value of x, and on its own that's good, we can predict how much of the variance of y is because of x. And I think this is just as useful, if not more so. So this is very useful in our example of cigarette smoke per day and life expectancy. Now, however, that is simple. We just have cigarette smoked per day against life expectancy. But as we know, things aren't that simple. We're going to have multiple different reasons that affect life expectancy. And it's easy to actually plug these into multiple regressions. So we take our standard equation, y equals mx plus c, and we can just modify this. So linear regression in its simplest form uses just one variable to predict the response of another. Multiple linear regression uses multiple variables to predict the response of one variable. Just as a little experiment, we can try to visualize fitting a line of best fit using 3 variables. Hopefully this works. And it's not going to work. It doesn't matter too much. I'll just kind of explain, so hopefully you can see, if in 2 dimensions, we've got y against z, we can see a correlation in our data, and that we could, this may not be the line of best fit, it doesn't look that great to me, but this could be a line of fit that you could plot. However, if you add a 3rd dimension, so it's a multiple regression, which goes into the page, actually, when you pan round, this becomes a surface. It's no longer just a line. It's just a surface. So regrettably, I can't show you the video, but as you project data into the x direction or into the page, this line of best fit becomes a surface. Doesn't matter too much though, because we can't really comprehend things above 3 dimensions. And if you're going to be doing multiple linear regression, you'll be doing it with more than 3 features, you upwards of 10, 20 or so on, and you definitely can't visualize this. So it doesn't really matter though, because the equation remains pretty simple. So if we had y equals mx and plus c on the end, for each new feature that you add or variable that you add, you just have another value for that and its coefficient. So it's really simple. So it's a nice, simple equation. So, if we had 4 features or 4 variables, this would be the third and this would be the fourth. And that means that not only things like SS fit and SS mean, they're easy to calculate, but R squared, when we're looking at the variance. So what we're really talking about here in multiple linear regression is we know that one variable on its own doesn't account for much of the variance in the response. However, multiple variables, they might contribute a small amount on their own. And so, that's where R squared comes in. So now that we understand how linear regression and multiple linear regression works, they're really simple. You're just looking for this equation. How good is our model? So in statistics, we will often talk about how good a model is. And so this means for regression, what is our line of best fit statistically significant? So try and unpick what this means. So if we fitted a line of best fit to data collected from patients with heart disease, would we be sure that that trend describes heart disease patients only? So yeah, in the general population, you might have found some trend. You've taken your patients with heart disease and you've looked at some of the variables that contribute towards heart disease, so smoking and so on, and you find some trend. You get a line of best fit. You've calculated R squared, so on. However, if you observe that exact trend in the population for maybe other diseases or so on, then maybe this finding isn't statistically significant. So we need to try and unpick what this means. And just a header up, I think you would have all heard about p-values. We're going to work through how we calculate the p-value for linear regression. Yes, and you may have heard something like this: a p-value less than 0.05 means our result is significant. So we need to try and understand what a sentence like this means. And when we're saying this, what we mean is that if we were to plot a line of best fit using variables for patients that have heart disease, and then we take many thousands of samples from the population at random, then our line of best fit for the heart disease group is only significant if less than 5% of random samples show a similar line of best fit. And this is important because, and we will revisit this at the end, if we plot a line of best fit with a large R square, i.e. we think we have a model which explains a lot of the variance in our dependent variable, we might think this is a novel finding. With a large R square, we've got this variable that we're interested in, and using our predictors, our variables, we can describe a lot of that variance, and you think you've solved the problem. But yeah, if you find the same trend, in other sections of the population, then maybe it's not significant. So how do we calculate the p-value for our R squared? So we know R squared tells us how much of our independent variables explain the variance in the dependent variable. So remember this. So R squared is the difference between variances in the mean, SS mean and SS fit, divided by the variance in the mean. And we need to introduce something called an F statistic, which will become a distribution. And so if this was the variance, the explained variance, well, the F statistic uses the unexplained variance. So F is the difference between variances in mean and fit, as above, divided by the unexplained variance. So, again, even if we plugged in 100 different predictor variables, we still might not explain 100% of the variance in our response variable. So this is what F tells us. It's the ratio of the variance between the mean and fit divided by the remaining unexplained variance, which is 1 minus var fit. Yeah, so F is equivalent to the ratio of variance between samples and the rest of the variation not explained by that model. And what we're going to do is we're going to compute F for our line of best fit, and then compute F in the case of these many, thousands of random samples. So let's try and visualize what's going on. So here, just to recap, we have a line of best fit. This is SS fit, this blue line. This yellow line is SS mean. So this might be our line of best fit. And we have a random sample on the right here. And we might conclude that in this random sample, which you would expect not to be as correlated as our sample on the left, you can see that actually we have large residuals. So again, this might consist of patients which had heart disease, only patients with heart disease. So you can maybe see a correlation. However, when you take random samples, data isn't as correlated you would expect. That's our hypothesis. But we can compute F for both of these samples. So it's, same equation. However, what you should notice is this in an ideal world, that for correlated data, var mean is larger than var fit. You can see that here, even in this case, var mean, all the residuals summed up and squared, is larger than var fit. So this means that we're left with a large number in the numerator. And var fit explains a lot of the variance. So because this is correlated data, var fit explains a lot of the variance. This means the denominator is small. So a large number divided by a small number will end up with F being large. And the flip side of this with our uncorrelated data is that, as you'll see, we know that in correlated data, var mean is large. But in this case, the var fit is also large because it's not a very good fit on our data. It's not very correlated. So we end up with a small number on top because these two values they converge towards being equal. So small value on top. And then because we have a lot of unexplained variance left over, we have a large number on the bottom. So F will be small for uncorrelated data and F will be large for correlated data. And we can, as we resample many thousands of samples, random samples in our data, in our population, we can actually form a distribution. So this is our model. We've computed F for our model where we have a pretty good fit. Our data seems to be correlated across the predictor variables, and then we'll take random samples and calculate F there. So as you can see, F overall should be smaller. This is our hypothesis. And we just keep sampling until we get to the stage where we have something that looks like a distribution. And this is called the F distribution. And the F distribution tells us the nature of how data is correlated and how often we will see correlated data. But I'll come back to that in a sec. We need to get this p-value. Okay, so we've got our F distribution. How do we calculate our p-value? So if we just take this blue area here under the curve, this represents 5% of the total area under the curve. The 5% of the area most shifted to the right of this curve. So, you can kind of see what we're getting up towards. When we say things like our p-value is 0.05, it's relating to this area under the curve here. So this is our critical value, or alpha, you might hear it sometimes called. That threshold 0.05, that is alpha. We want our p-value to be less than alpha to be significant. So the p-value is equal to the area under the curve greater than the F statistic divided by the area less than the F statistic. So this blue area divided by this white area. And in our case, we've arrived for our fitted model a value of F which equals 6.2, and it may correspond to the area under the curve from this onwards to the right, i.e. here. So when f equals 6.2, this corresponds to this much of our curve. And what we do is we divide the area, which is blue, divided by the area, which is white. And that's how you find your p-value. So when f equals 6.2, p is found by dividing the new blue area by the white area. And remember, this f critical relates to this 5% random chance. So if p is less than 0.05, then we have a statistically significant result. And of course, you can just see it here. If this is our threshold, if f equals 6.2, and this is the corresponding area under the curve is this, then you can see that it's less than f critical. So that's how you find the p-value. And when people say to you, my p-value is this, in linear regression, this is how you would calculate it. This F distribution is interesting, actually. So there's a few things you need to look at. Let's just talk about the degrees of freedom. And degrees of freedom is how you can introduce more variance in your model. So we know that if we have lots of different predictor variables, for example, then this is going to increase the variance overall in our ability to predict against our response. So there's a few other things. You could have a number of data points. They would increase the number of degrees of freedom, and also the number of features. They would increase the degrees of freedom. But let's just talk about what that means. If we had 2 data points only, our degrees of freedom, the equation for this is n minus 1. So degrees of freedom is n minus 1. But why is this important? Why are degrees of freedom important to us? Well, in this case, when the degrees of freedom equals 1, that means you can plot a perfect line of best fit, perfectly correlates. If we had 2 different data points, pretend this is on a different graph, again, you could have perfect correlation. So where degrees of freedom equals 1, perfect correlation, this doesn't tell us much, it's a self-fulfilling prophecy. So there's no difference in variation between 2 random samples of 2 points. And both these lines perfectly fit. We can't say that one is more statistically significant than the other. This is what this yellow line is. With only 1 degree of freedom, df, there is no difference between random and correlation. You see, so as we slide into more random data or less correlated data down to the left, is an identical distribution as if we had highly correlated data with 2 data points. Okay, so that's why this curve looks a bit odd. But as we increase the number of degrees of freedom, we'll start to see this F distribution, and it becomes quite tight the more degrees of freedom you add. So, our average would explain the majority of our samples as we keep adding degrees of freedom. And just to illustrate that, how we can compare. So we have 2 samples. Again, this would be our correlated data. Maybe this is people that had heart disease only, and this is our random sample. In both cases, degrees of freedom equals 5 because we have 6 data points. But clearly, we can see that with more than 2 points, it's possible to see a difference in variation between the group of interest and the group sampled at random. So, if you only took, on the left-hand side here, if these 2 patients, the only 2 patients you collected data on, they both had heart disease, and then you went and chose randomly in the population 2 other people, you would know that you don't have enough power in the study to allow you to say which one is more significant in terms of what you're predicting. But so you need to increase the number of degrees of freedom for this to happen. So, yeah, so as you keep increasing the number of degrees of freedom, and again, 2 ways of doing this is to increase the number of data points. Also, you can increase the number of features you add into your model. You'll see that the F distribution converges towards this green shape here. And I suppose, why is this a taller curve than some of these, a taller, narrower curve than some of these? this just reflects the fact that as you increase the number of degrees of freedom, or number of features, number of data points, you expect more precision in your model. So, again, this is a narrow curve. The standard deviation in this green curve is lower than any of the other curves. It just tells you that the more data that you add into your model, the better the estimate will be. And the reason why I really like this F distribution is that, so if we remember that as we have more random data, so more correlated data as we go to the right and less correlated data as we go to the left, the F distribution tells us that in life, there are 0 true random events. So, nothing is true random in nature. That's what this F distribution tells us. What we find, though, is as we start to increase the more correlated data, we've not gone too far up the scale of correlation, but we actually find that in life, there are lots of weakly correlated samples or examples of correlated data, and only rarely do we get strongly correlated data. So this F distribution universally says that in nature, there's no true random, but rather we have an approximation of a normal distribution of weak signals with the odd strong signal, which is these signals on the right. So you can think of any situation in life where this would apply. So I think that the F distribution is a pretty cool distribution. Now, degrees of freedom. How do we handle this with F? So we can actually scale F by our degrees of freedom. And this is what you tend to see in your output, and we'll see this in our notebooks. Why do we need to do this? Why do we need to scale F and R squared by our degrees of freedom? So if you look at our equation for multiple linear regression, you're just adding in variables. It's y equals mx plus c plus nz plus other variables. So we keep adding variables in, and this increases our degrees of freedom, as you see here. And R squared will always increase as we add variables. Now this becomes a bit of a problem, I think. R squared never decreases, even though that we know that some variables will be useless to predicting life expectancy. So we might have included useless variables in our model. However, they will increase R squared. No matter how little, they will always increase R squared. And this inflates R squared somewhat. So what we need to do is to penalize this, or adjust R squared to account for this phenomenon. And what we can do, we can just arbitrarily penalize R squared based on the number of samples or the number of features in our model, n and k. And what we can notice is that as k or n gets large, R squared adjusted becomes smaller. So we're arbitrarily deflating our original R squared to achieve this R squared adjusted. And that is purely because of the fact that multiple linear regression is just additive in nature. So in summary, regression fits a line to your data, a line of best fit. It uses the sum of least squares to optimize m and c in the equation y equals mx plus c. R squared tells us how much of our variation in the dependent variable is explained by our independent variables. F is the ratio of the variation between samples and the remaining unexplained variation after regression, and we use F to calculate our p-value. And of course, the p-value tells us how significant our result is, or how likely we would expect this result. So that's it for the theory side of things. I'm going to quickly take you through the notebook, which is on Kaggle. So this Kaggle notebook is on the front page. I'm still editing it, don't worry about it. So if you just open up the first notebook on the Kaggle front page, make sure you've refreshed so you're seeing the latest version. And the R code is very simple. It's really simple. And I guess for some of you, this is the first time you might have seen any R code. So we're just going to import a few libraries to start off, and I'll explain what each of those are. So we have the US National Health and Nutritional Survey, which they have is mainly a data repository than anything, and they've put it into an R package. You can see more about this if you visit this YouTube channel, YouTube video. And then library tidyverse. So we're calling in this library called tidyverse. For those of you that know, tidyverse includes lots of useful libraries within R that people use. So for things like data manipulation, even machine learning itself. And in general, whenever I'm coding in R, I always start off by importing the tidyverse library. Okay, so we attach our data. And it's a large data set. You can use all of the rows if you really like, but I'm just going to use the first 1,000 just to demonstrate the principles. And you can explore your data in R in a few different ways. So head will just give you the first 6 rows of data, which is this first output. You can see all the various columns that we have. Scroll all the way across. And another useful thing is the str function. So this tells us the data type of each column. Actually, this is unique to Kaggle. If you do head df in RStudio, it won't tell you what all the data types are across all of the columns. You would have to use strdf, but in Kaggle, I think it's fed it into something like the data.table package. It tells you what each data type is, which is useful. And this is useful because in regression, linear regression, we're only interested in continuous variables. So, int, this is continuous variable. FCT, this is a factor variable or categorical variable. So we're not interested in these for linear regression. So yeah, it's a lot of columns. And really, linear regression is simple. It's just the LM command, linear model. And we are going to look at the relationship between weight and height. So weight is going to be our dependent variable, our response variable. And we're going to see how well height predicts weight. So, we have our original data frame df, and we just use this formula as the first parameter on this data frame and store it into an object called lmwh, lm weight height. So let's just go line by line. Before we store it into an object, we can see what it's doing. Just tells you, there you go. The slope m is 1.043 and the y-axis intercept is minus 9.4. Remember again, this is a theoretical lower estimation of what it would be. No one has a height of 0. So this is why this looks strange. Okay, so don't worry too much about it. So we'll store it into an object. And then we can do a summary. So summary is a really useful command in R. You can plug in many different types of objects into the summary function. And because R, the philosophy behind R is lazy evaluation, whatever object you put in, the summary function is going to guess what type of object it is and spit out what it thinks is an appropriate summary. So there you go. That's our regression. And just to demonstrate that lazy evaluation in R, we could just do summary of df. And there you go. So this is quite nice. We don't have to define things. R is doing a lot of work for us under the hood. But let's just return to our linear regression. Go through it. So we have things like our max and min residuals. So we know how to calculate our residuals. That's the first thing. In this table here, we have our coefficients. So, what we were looking at was the intercept. So this is in y equals mx plus c. This is c. And this is m. And we have our things like our standard error and p values as well. So we know that this is significant finding. I would say that so it almost seems 1-to-1. So as you increase 1 unit in height, you get a slightly higher increase in the response variable. And we have things like, where is it? So r squared and adjusted R squared. So remember, this is taking into account degrees of freedom. In this case, it was only one degree of freedom, but there are many data points, so this shouldn't change too much. Again, also we have our F statistic. So this is quite a big F statistic. I was using values of 6.4, I think, in the slides, but F can be really large. Now, multiple linear regression, it's just simple. So we take our formula. Remember, we just had this before. We can just add in a new variable. Really, really easy. So add in total cholesterol. So we will run this, and what we're going to do, we're going to plot our results. So first, just store our object and see the summary. There we go. So what we can see here is that total cholesterol has a higher correlation with weight, which seems reasonable. Is a better predictor of weight than height. And we can plot this. There you go, there's our data, and we'll add our regression lines. Remember, we stored our regression object in multi-LM, and we're just going to create a new line on top using that. And we get an error. I will figure that out in a bit. We just see. There, yeah, sorry, it's just a warning, it's not an error. So yeah, so even though we've plotted weight versus height, this regression line takes into account total cholesterol as well. And if we just compare this when you only do it with weight versus height, the y-axis intercept in the linear regression case, if you compare that to multiple regression where you take into account total cholesterol, you can see it's a very slight difference, but you can see the difference there. So that's just reflective of the fact that in regression, our regression model, we've taken into account total cholesterol. And it might look a bit strange because you might think, oh, well, I add more variables in. Surely the line of best fit should look better. And I would say this looks worse than in the linear case. That's purely because we're plotting weight versus height. You would need a 3D plot to really assess this. But I wouldn't, this is just to demonstrate how you plot things in R. I wouldn't get too hung up about plotting the results of your regression. You just need to look at the output in this case. So just using a different data set, R has many inbuilt data sets. There's one called empty cars, which we can look at. This takes in different cars, and it's got things like miles per gallon, weight, drag. I actually don't know what a lot of these are. I'm not really into cars. Carburetor type, maybe. So, we can do linear regression on this, only on the continuous variables. So, even though this is a number gear, so these are often called ordinal. So they do appear continuous, and they have a continuous scale. But as you can see, there's a big difference to this. Almost as a category, and it is in a way. How many gears do you have? And even though it's a continuous category, it's not quite the same as the precision that we have in maybe weight category. So yeah, these are sometimes called ordinal. You technically can put them into your regression model. I don't think they would be a more crude way of measuring variance because this doesn't have as much detail as WT. But anyway, we can put these in. We could technically use all of these variables. And what we're going to look at is MPG. So this is our thing we would like to predict. And we just plug in. So some of you may already be aware that instead of typing all of the columns in, because there are quite a lot of columns now, if you just say MPG tilde dot, this uses all features. It's shorthand to use all features. And we can, I didn't save it, sorry. Let's just run this. Oh, yeah, that's right. It needs to be changed to that. So the wrong name. So LM cars WT. And there you go. So we can plot this as well. So the question asked here, what was, find the variable most correlated with MPG, or has the, how do you explain it? As you increase one unit of a certain feature, you increase MPG the most. That's what we're saying here. So we can look across and look at our regression, and we're just looking at the magnitude here. So what you might have looked at was AM. This was the largest of the positive coefficients. If you look at WT, the magnitude of this correlation, and the magnitude of this coefficient, is actually larger than this. It's just a negative correlation. So that means as you increase the weight, you lower the MPG higher than you would if you increase AM. So actually, this is the variable which carries the most weight in predicting MPG. And again, we can just plot those together. So we'll plot MPG against weight. And there we have it. So yeah, it's a really nice correlation there. So that's linear regression theory and the notebook. And next we will look at logistic regression, which is where you have a binary response variable and your predictor variables are also continuous.